Okay, ladies and gentlemen, welcome back to P-Dog Does Science, and we've got our new chapter, Chapter 5, which is about electrons, quantum mechanics, and the modern model of the atom. So the first thing we're going to do is review some of the older models of the atom that we've come across until we have the one that we have today. And so you may remember that our first model of the atom, our first official model of the atom that was truly an atomic model, came from John Dalton. And Dalton's model was that atoms were hard, unbreakable spheres, and that there was uh, one kind of atom for one atom for every kind of element. One atom per element. Okay, and then later on, when we started discovering that there were other particles and other phenomena that had to come from the atom itself. Thomson discovered the electron and came up with the plum pudding model, which had electrons embedded in a core of positive charge. Okay. Then after Thomson, in 1911, Ernest Rutherford discovers the nucleus of the atom through his gold foil experiment in firing alpha particles at a sheet of gold foil. And he felt that electrons would actually orbit the nucleus in a circular path, and they would stay in circles. Now the new ones that we haven't talked about yet, the next one is the Bohr model, named after a Danish physicist named Niels Bohr. And he stated that electrons that are traveling in these circular paths can gain or lose energy by changing orbits. That they can absorb some energy, and they'll actually change to a larger orbit around the nucleus of the atom. And then finally, in 1926, we have the electron cloud model, where electrons don't have a predictable path, and they exist in regions of high probability space. And I want you to rearrange that if it's not already rearranged on your paper. That these are regions, so high doesn't go there. These are regions of high probability space called orbitals. So let's see if we can try that a different way here. Let's clean this up. A region of, well, that's not there, and that's not there. So they exist in regions of high probability space called orbitals. And we will demonstrate that in class. We will try to demonstrate that in class in the next couple days. Okay, so we need to go back and we need to discuss the Bohr model of the hydrogen atom. It was named for Niels Bohr, who was a Danish physicist, and his theory is that electrons orbit the nucleus in a circular path at different distances from the nucleus. And the arrangements of the electrons determine the kind of atom and its ability to react. And his theory was based on the Bryce-Line spectrum of hydrogen, which we will discuss in section 5.3. And we'll get more into that in a minute. But here's the idea. Electrons exist at the lowest possible potential energy positions with respect to the nucleus. This is called the ground state for the electrons. They experience what's called a quantum leap, and this is not talking about the 80s TV show. We're talking about when electrons gain energy from a heat or electrical source, they jump to a higher energy distance away from the nucleus. Okay? This is an excited state where they gain potential energy. When these excited electrons lose energy from the quantum leap, they return to their lowest energy state. So think of it as something like this. You have an electron. That's not a very good drawing. Let's try this one more time. There we go. Let's try this. Okay, so we have this electron, and our electron is going to jump from a place that's close to the nucleus, which is where electrons like to be. And if the imagine you have a little 6-year-old, and she's running like crazy, and it's easier to contain the little kid in a big circle than in a smaller circle. The kid isn't going, if it has a lot of energy, she's not going to be able to stay inside of a really circle real close to mom and dad. She's going to want to expand and go out and create big circles around mom and dad. And so when the little kid gains energy, gets more energy, she will jump up to she'll move out to a larger energy circle. And that's what electrons do. When they absorb energy, they jump to an outer orbital. And then when they calm down, they return to either a lower energy level, which is if they calm down a little bit, or if they calm all the way down, they can return to what's called their ground state, which is their base level of energy. Okay, so any state above their ground state is an excited state. But they can also drop down to intermediate places depending on how much energy they have. However, these circles are very specific, and they equal very specific amounts of energy. And we're going to get to that in a little bit later about how much that energy is. And so we go on to page 2. Okay. Now, when they release this energy, when they fall down, or when the excited electron or the excited little child returns to its ground state or its low energy, it releases this energy in the form of electromagnetic radiation. Okay, and very often it can be visible light. In fact, all visible light comes from an excited electron returning to a lower energy state. This produces the barcode of the element that is known as the bright line spectrum. Now, the math only works for hydrogen atoms. It only works as hydrogens increase and decrease. They increase and decrease in energy, but the reason it only works for one hydrogen is why? What do you guys think here? So pause here and take a guess at it. Well, what'd you think? Okay, how is hydrogen different from all other atoms? There's only one electron. And because they only have one electron in hydrogen atom, it's very easy to track. It's the one thing that's gaining any energy or losing any energy. And there's no electrons interfering with each other. And this barcode, this idea, brings us to we have to come up with some sort of model that's going to have more than just the one electron coming from hydrogen. And that brings us to the quantum mechanical model of the atom. Okay, so as we start accounting for more electrons, we come into the quantum mechanical model. It has the same components of the Bohr model, yet it describes the nature of electrons differently. Electrons do not orbit the nucleus in a definite circular path because of the repulsion and attraction to each other and the repulsion and attraction to the nucleus. They occupy what are called orbitals. So as stated by Bohr, Bohr said that there were orbits around the nucleus. And that works just fine for the hydrogen atom. However, for other atoms, it doesn't quite work the same, and we have to come up with some other way of explaining how electrons move. So, electrons are found in regions of probability space called orbitals, which are found in energy levels. Now, orbitals are regions of space with a definite shape, size, and energy, but they don't describe how electrons move. They just describe where they can be found. Okay? But in these regions are called electron clouds. They are high probability regions of space that determine the size and shape of the orbital. And here's the idea of the high probability region of space. Imagine that you are in a completely dark room with thousands and thousands and thousands of moths. And as we all know, moths are drawn to light. And so in the middle of the room, there is also a single really bright light bulb. Now the light bulb is only so big, and so when you turn on the light, the moths flock to the light. They go to the light. And however, there's so many moths, and there's only so much room around the light, that there will be the huge concentration of moths around the light bulb, and as you move away from the light bulb, you still have moths, but you start getting fewer and fewer moths as you grow a sphere around, a spherical region around the light bulb. Now, there would be a sphere that you could imagine that would hold 90% of all of the moths that are attracted to the light. Okay, the other moths would be somewhere else in the room because they're moths and they're relatively unpredictable. But there would be this sphere, this region of space, where if you were to pick one particular moth, 90% of the time it would be in that sphere. That sphere is a region of probability space in order for you to find that moth. The same thing goes with electrons and electron clouds. The clouds themselves are regions of probability space where there is a 95% chance of finding an electron with that particular amount of energy. It's sort of difficult to draw, and so I have a problem with that. But in here in a minute, I have some animations that I think are going to work for you guys. So, these regions of probability space also have, there's general classifications for these. And the first general classification is called a principal energy level, also known as an electron shell. Okay, each energy level is limited to certain numbers of electrons. And these certain numbers of electrons are the only electrons that are allowed to have that amount of energy in that space. Now, the first energy level is the lowest in energy, in potential energy, followed by the second energy level, which has more potential energy, followed by the third, which has even more potential energy. And these levels have letter distinctions starting with 1. Okay, and so the first energy level would be K, and the second one is L, but you don't need to know those so much. These are not so important right here. These letters right here. The maximum number of electrons possible in any principal energy level is determined by the formula 2n squared. And this is where n is the energy level. Okay, so for example, in energy level 2, in the second energy level, okay, so we're going to have energy level 2 and 4. We'll do the math for these. Energy level 2 will result in 2 times 2 to the second power. Okay, well, how many would that be? That would be 8 electrons. In the fourth energy level, it's going to be 2 times 4 to the second power. 4 squared is 16, times 2 is 32. So there will be 32 maximum electrons in the fourth energy level. Now, these primary energy levels, or principal energy levels, have sublevels to them, and these have distinctive names. Okay, they contain one or more sublevels. They are called S, P, D, and F. And I don't remember what those stand for. I can look those up, but it's really not important for what the SP and the words that they stand for, as so much as the shape of the orbital, which is truly what they represent. Now, each principal energy level has the same number of sublevels as the energy number. So, the first energy level has one sublevel, and it's called S. The second energy level has 2 sublevels. They're called S and P. The third energy level has 3 sublevels, and it's called S, P, and D. And the fourth has 4, and those are S, P, D, and F, and so on. And the fifth would have 5, and that would be S, P, D, F, and G. And it goes G and H and I, and so on from there. But we will not be dealing with G, H, and I, and so on. We'll only be dealing with S, P, D, and F. Now, within each sublevel, there are regions of space where electrons exist most of the time. These regions are called orbitals. These are the regions of probability space where electrons with a certain amount of energy usually exist. Okay. These orbitals have names that explain their position inside the sublevel. For example, the P sublevel has 3 orbital orientations: an X orientation, a Y orientation, and a Z orientation. And they are at right angles to each other in all three dimensions. Okay, and each orbital shape has a set region of space. The S sublevel has 1 orbital and it's spherical. The P sublevel is bilobed. There's 3 orbitals. And I'll show you a demonstration of those in class and I'm going to show you an animation here that's going to have, it might be a better example for what we're talking about. Then there's D. The D sublevel, there's 5 different orbitals in the D sublevel, and each one of those has a very complex pattern to it. And F is even more complex, and there's 7 orbitals of those. And only two electrons can inhabit each orbital. Okay, regardless of the type of sublevel. So, if there's in any particular orbital, only 2 electrons can go in there. So in the S sublevels, there's a total of 2 electrons. In the P sublevels, there's a total of 6 electrons. 3 orbitals, 2 electrons apiece. In the D sublevels, there's 10, and the F sublevels, there's 14. 5 orbitals times 2 and 7 orbitals times 2. Now, here's the idea of why they have these shapes. And here's the basic shape of a 1s orbital here. Okay, it has this very basic general vibration to the orbital. And it's here that we need to mention a little bit about electrons and how all matter has a dual nature to it. Matter can either be thought of as a particle or it can be thought of as a wave. And if we study matter as if it was acting like a particle, it will act like a particle. And if we study matter as if it was acting like a wave, it will act like a wave. But the two ideas don't mesh with don't mesh very well with each other. The shapes of the orbitals are based on the wave nature of the electron. And so we have this repeating pattern, this harmonic motion that we get. And this would be the 1p sort of shape. And you can maybe see how you can imagine how it could make a sphere of some kind. And that's sort of what this looks like. Okay, then if we increase the energy a little bit, we'll go to the next larger s orbital, and it looks like this. Now notice, you can maybe even see two shapes in it, or at least a ring inside, where it's a very simple double vibration here. Okay, but there's another kind of energy shape at the second energy level, and it's this. This would represent what the p sublevel would look like, and notice how it's twisting through the middle, and you kind of have a region over here that is let's see if I can. You have a region over here, okay, and another rotating region over here, and then a spot right here in the middle that doesn't move, and that's called a node. And there's really no region, there's no space there for the region. It just sort of rotates around it. Okay, so that's another shape that gets represented, and we can revisit this a little bit later. I want to show you a couple more shapes because they start looking really, really cool. Okay, here's some more shapes as we go about them. This one up here is another sort of spherical one. You can see how it compares to the other ones. How we have the very basic one, and then we have a double wave, double standing wave. Then we have a triple, up and down and up, or down and up and down, or up and down and up, or up and down. Okay, or this one just has an up and a down, or a down and an up. Okay, so there's just two, and here's just one basic up and down. Okay, those are all actually the same shape. Those are all a spherical shape, and they're called s orbital. Then we have the p orbital, which has this twisting motion to it. See if I can get this the same size here. Where it has a general single twist, or this one has like two twists in it. If you guys can see those. Okay, and then we have another one that kind of looks like this, and this is the next energy level up. But if you notice that we have an extra layer of twist in there, so this one has alternating. There's two alternating ups and downs, so this one just has one alternating up and down. This one has three alternating ups and downs. Okay, and this is just an increasing amount of energy involved in the vibration. Okay, and as we increase energy, though, we also come up with another shape, and that's this one. Where now we start twisting in multiple directions. And this one. And you can see how one is more energetic than the other because it has more loopies to it. Okay, we will revisit these. We will revisit these when we start getting deeper into SPDNF, and I'll have you guys identify which one's which. Okay, which brings us to just about the end of 5.1, where we talk about electron spin. And electrons spin on their axis, which creates a tiny magnetic field. Electrons have an electric charge, and any kind of moving electric charge creates a moving electric field, and a moving electric field creates a magnetic field. And so, electrons, as they go into the orbital, if you have a spinning electron, or all electrons spin, because of that, they have a particular magnetic field around them, and they can only be joined by electrons that are creating an attractive magnetic field, which means they have to have a spin that is in the opposite direction. And so only electrons with opposite spin directions can occupy the same orbital. Only electrons of opposite spin can occupy the same orbital because of this magnetic field. That's going to do it for 5.1. The assignment that I have for you is section review 5.1 and this workout of the book. And there are some problems in the book that you are going to need to show your work on. So please be sure to do that. So that's it for 5.1, and this is PDog signing off.